Hello, everyone. Welcome to April. Hope you saw kind of the lecture updates post earlier this hour. So today, we're starting our kind of guest lecture series. Today, we're very happy to have Dian Wang, who is a PhD candidate working with Rob Platt and Robin Walters on Equivariant RL for robotic manipulation. The one indication of whether Dian has done a good job today is whether you could recite the definition of equivariance by the end, or rather at least give us an informal kind of recitation of that. Actually, I was thinking earlier, I was like, so before your PhD here, like you were a master's student in computer science as well.
Yeah.
Did you actually take this class when you were?
Yes, I did.
With Rob?
The very first
one,
yeah.
It was still like 7180, right?
Yeah.
So here you see kind of one of our successful alums of this class. So maybe it's your turn here in 5 years. But today, very happy to have Dian. And I think feel free to kind of, as usual, jump in with questions. I'm sure Dian can handle them remarkably well. So, all right.
All right. Thanks a lot, Lawson, for the nice introduction. And good afternoon, everyone. I'm Dian, and I'm a fifth year PhD student here. And as Lawson said, I was a master student before the PhD. And I took this class, and it's very honored to come back to present to you our stuff in Equivariant RL for robotic manipulation. So I guess you guys have already learned about the basic ideas of deep RL, right? That's great, and I guess most of you might already know that RL has all kinds of applications like the game of Go and whatever. And today I'm gonna be talking about the application of RL in robotics, and hopefully that could give you guys a sense of like what RL can be really applied to some real world problems. Hopefully this is gonna be interesting to you guys. And yeah, feel free to jump in with any questions in the middle of the lecture. So recently there has been a lot of success in using machine learning methods or deep reinforcement learning methods for robotics. Here I have two examples of the recent works. On the left, we have a robot arm that's trying to pick up objects in the tree in front of it. This is purely trained from reinforcement learning algorithms, learning from scratch, doing exploration, just like what you guys have learned already. And at the end of learning, this agent could actually pick up objects really well, even though some of the objects might not be seen during training. It can still handle them and pick them up in front of the tree. And on the right, there's another example for what we call locomotion. Basically, you want to teach the robot how to walk. And this is also trained entirely from scratch in the real world using reinforcement learning. So those methods were actually pretty working very well, and they were all powered by what we are learning in deep reinforcement learning. But there's one key question for those methods, which is those methods are very data hungry. So for the grasping robot that I showed on the left before, it actually took the folks from Google 4 months to collect 800 robot hour data using 7 robots. This is extremely expensive. I guess the only place that you can do it is in Google. There's no way that in a standard lab university like us can have 7 robots running for 800 hours, right? This is crazy. So even though it worked very well, there's this downside of acquiring really a lot of data for the RL agent to do exploration and exploitation. So how can I do it? Yes. Yes, exactly. Yeah, there were all real world robots, and they were trained from scratch in the real world. And you make a great point. We can use simulation, right? So we can train an agent in the simulator and then transfer that policy to the real world. This is a great strategy, and a lot of people are doing that. But the problem with that is that first, because we work in the field of robotics, in the simulator, you actually need to simulate the physical contact between particles or whatever. It's actually not fast enough still. Also, you need to handle the so-called thing to real gap, where the dynamics that you are facing in the real world might not be exactly the same as you have in the simulator. So once you train the policy in the simulator, it can work very well. But if you deploy in the real world, things can happen, like the friction on the table are different. You have a different gripper. Gripper is, the thing at the end of the robot that actually do the grasping, or the lighting conditions are different. There are all sorts of problems that can make the algorithm not work in the real world. So the question here becomes, how can we improve the learning efficiency for deep RL? Is there a way to learn, a reasonable, good policy within a reasonable amount of data? So here is using 800 hours from several robots. That's crazy. We don't want to do that. We want to learn, for example, with 100 demonstrations or 100 like data from the real world. That's more manageable in place that's not Google. So my research or the in our group, we try to use symmetries to solve this problem. So imagine that you are a robot and you are in front of a tabletop with 3 different objects on it, and you want to pick up the green trapdoid. This is a simple task. It can also be formulated using reinforcement learning. You can do like a multi-arm bandit, or you can do standard reinforcement learning, whatever. This is a very, very simple task. Now consider a different state that is a rotated version of that same state, right? So what you want is your policy to execute the exact same action, but rotated by the same rotation, which is applied to the state, right? So those 2 different states are essentially the same. They are just 90-degree rotated versions of each other. You will want your policy to automatically generalize from the left state to the right state. But unfortunately, this is not typically what deep learning methods do, right? So if you guys have trained like say a deep RL agent or whatever, it's not gonna have this level of generalizability, right? In the standard machine learning methods, the left state and right state are gonna be treated separately as 2 different data, and the model need to learn from them separately. So our goal here is to design algorithms that can automatically generalize over symmetries. So if we learn from the left state, we want the agent to generalize to all of the rotated versions of the same state so that we can greatly improve the efficiency of our data. So is it clear so far? Any question? Great. So before we talk about how we actually do it, I need to fill in some like backgrounds of what we really mean by symmetry. Right? Symmetry is like a concept that's sort of abstract, and we need to have more of like a theoretical definition of what we mean by symmetry so that we can actually build algorithms to implement it. So basically, when we talk about symmetries, we typically mean invariance and equivariance. And the following slides, I will talk about what we exactly mean by them. So imagine that you have a symmetric group. If you have learned abstract algebra or group theory, you might know what a group is. If you don't, that's fine. Just think of it as like a space of all the rotations that can happen in your data. And consider f of x as an arbitrary function, right? Now imagine that I'm building a cat classifier. I just train f based on a lot of images of different cats, and now taking one image of a cat and I rotate it, that doesn't really change the fact that the input image is a cat, right? So our cat classifier should still tell us that the input image is a cat, even though the image is rotated. That is what we mean by invariance. Applying a transformation G to the input x of our function won't change the outcome of the function f. That is invariance, and that's the the basic situation of when we say a function is symmetrical. Here we can say the function f is symmetric over rotation. And there's another scenario which is equivariance. Here we have a different, we have a similar definition as before. We have a symmetry group, which can be the space of all rotations, and we still have a function f, but now let's define f as a CAD segmenter. So basically, we want to label the pixels where label all of the pixels that belongs to a CAD and not label the other extraction pixels, right? So in this case, if we still apply the same rotation to the input image, we will want the output of our function to rotate accordingly, right? Because when the CAD input image is rotated, the output segmentation mask should rotate by the same amount as the input image. So that's what we mean by equivariance. Basically, it means if we apply a transformation G to the input X, then computing the result of function F, that should be the same as computing the result of function F first for the original input X, then applying the rotation G. So if you write it down as the equation, let's basically look at this. If you apply some transformation and rotation to the input of F, that's the same as first passing through the function F, then applying the rotation G. Is it clear so far? Am I? Yes.
What do you mean by transformation? Instead of linear transformation, like any matrix?
Yes, that's a great question. So basically here, transformation is still like a concept. It's a still abstract concept. You can think of it as a rotation. You can think of it as the two transformation that involve both rotation and translation. You can also do it as what you said, applying a linear transformation. For example, we can define a linear matrix that apply to our data, which is a vector. Later on the slide, I will talk about those scenarios. But here, let's just assume that it's a rotation, or it's a rotation with translation, or even flip, whatever. Thanks. Yes.
Oh, sorry, just for future questions, can you just remember to repeat the question? Because otherwise it doesn't come up on the.
Oh, yeah, okay, thank you. Yeah, sure. Okay, great. So this is, equivariance and invariance. That's the, let's say, the mathematical definition of symmetry. So here we would want to apply a network that is equivariant when our problem is equivariant, right? So for the two examples I was showing, the CAD classification problem should be an invariant problem. And if we use an invariant network for solving it, it could improve the generalization. We don't need to look at the CAD images from all of the different angles. We just need to learn from one particular angle and we'll generalize over all of the angles. Similarly, if we are doing CAD segmentation, this is going to be an equivariant task. So we can use an equivariant network. And then we don't need to learn from all of the different rotated CADs. That's our goal. We want to use that concept in robotics to improve sample efficiency. So in today's lecture, I'm going to be talking about 3 different projects that we have been working on along this line of thought. The first one is the most important one, which is equivariant reinforcement learning in robotics. I'm going to be talking about multiple projects that use symmetries in RL and apply it to robotics. And then I'm going to talk about how do we handle latent symmetries. Sometimes there might be a mismatch between the symmetry that exists in your model versus the symmetry exists in your problem, and what we do when we have that kind of scenario. And in the end, I will also quickly cover equivariant behavioral cloning. This is just a fancy word for supervised learning. So here we are learning reinforcement learning, right? And then supervised learning is just another way of learning a policy in the field of robotics. So similar concept of what we discovered in equivariant RL can be applied in equivariant behavioral cloning as well. And we also explore a little bit on that. Okay, let's jump into it. First, I'm going to be talking about what we call group invariant MDPs, which is sort of the theoretical grounding of most of our methods. I guess you guys have already learned about what an MDP is, right? So this is going to be a special type of MDP that contains symmetry in it. So imagine that you are, you are robot arm and you are in front of an object, and you want to find the orange object and then push it, right? So assuming that the robot pushes the block a little bit to the downside of the workspace, and we end up with a new state S prime. So we start from the state S, we apply a pushing action A, and we reach the new state S prime, right? This is just a transition in the MDP that is describing our problem. Now let's imagine that there's a rotation that's applied to our world. That means both the gripper and the objects are rotated by the same amount. So here you can see my finger got rotated from here to here, and the object got rotated from here to here. So the state is rotated by some certain degree, and then we have this new state. We can describe it using G dot S. So G is the rotation that got applied to the state. Now, if we apply a pushing action that is also rotated by the same amount, right? Before we were pushing from top to bottom. Now we push from left to right. So this is a rotated version of the same action that we applied before. So what we end up with a new state, we call it S double prime. But we will see is that it's actually the same as applying the same rotation to the next state S prime. So basically what it means is if you apply a rotation to both the state and the action, you actually got the same transition as before, right? So if you write it as the definition of a transition function, that means you apply the same rotation to your state, your action, and your next state, the transition probability won't change. Of course, there are some assumptions underlying the equation. For example, the friction must be the same across the entire world or whatever. But that's typically a valid assumption. You don't typically see a table that has one friction parameter on the left side and another friction parameter on the right side. This is extremely uncommon. Even though that happens, you might have some like visual features of the table that can tell them apart. Typically, if you have a table that looks the same, then it's going to have the same friction across the entire table. So normally, this is a valid assumption of the world. So this is the symmetry in the transition function, which exists in a lot of problems in robotic manipulation. And also a lot of times we also have the reward environments. For example, our goal for the robot might be picking up an object or push an object. A lot of times it doesn't really matter where the object is. We just want to pick it up, no matter where it is. So a reward, the same reward, is always going to be assigned when the robot finishes a task, but it's kind of orthogonal to where the object is relative to the word. So we can also write down the reward function as an environment function. If you apply the same rotation to the state and the action, the reward function is going to give you the same reward. So if we can have those two assumptions to our MDP, we could prove that the optimal solutions for the MDP is also going to be symmetric. What I mean by that is that if you think about the optimal Q function of the MDP, it's going to be group invariant. So if you apply the same transformation to the state and action, your optimal Q function should give you the same Q value. And similarly, for the optimal policy function, it's going to be equivariant. If you apply a transformation to your state, you will want your policy to output an action that's rotated as well. And here I'm going to give an example on that. So here, imagine we are training this policy network, right? And if there's a rotation that's applied to the input state, we will want our action to transform accordingly, right? So if the object is rotated in the world, we want to rotate our grasping policy, let's say. So this is the equivariance in the policy function. So we think of it in another way. That means if you apply rotation to the state first, then sending the rotated state to your optimal policy function, that's going to be the same as sending the unrotated state to the optimal policy function, and then applying the rotation to the output action. This is the symmetry in the policy function. And then in the Q function, when we have the same rotation, that's applied to both the state and the action, meaning like we pick up an object here versus we apply the rotation to both the state and the action and pick up the object here. They are essentially the same, and the Q function should give us the same Q value at the end of the network. Great. So this is question.
Do you want to keep all the trajectory which can get you from starting state to an ending state, but the same, even that the transformation that you take from one state to another are what's the property that you have for that?
The property that MDP have in order to use this equivariant in the yeah. Okay, so the question is what's the property that the MDP need to have in order to use this strategy? So basically, the property that the MDP need to have is this transition invariance and reward invariance. So if your MDP has an invariant transition function and reward function, we can derive from those two equations and show that the optimal solution are also going to have the same symmetric property. Does that answer your question? Great. Okay, great. So now we know that our problem has some symmetry in it, and we can take advantage of that symmetry by deriving the solution into the metric solution. Now, how do we actually implement that idea? The first project I'm going to be talking about is equivariant actual graded methods. Basically, our goal here is to enforce such properties inside the network. Right? We already know that what symmetric property that the optimal solution should have. Now we just need to take advantage of that property. Does anyone want to make a guess of how do we actually do that? Or even though without considering doing that inside networks, can we do that from the data side or whatever? Anyone want to make a guess? Yes.
You perform some sort of state aggregation that kind of collapses every transformation.
Yes. Exactly. That's a great answer to that. So sorry, what was the name? Arun just said, can we perform some state aggregation that bring all of the rotated states into the same one, so that we only need to learn that. This is a great solution. And actually, in the literature, a lot of people are doing that. They call it canonicalization. Basically, you transform all of your data to a canonical frame. Let's say that's just the frame what's the object supposed to be in. And then we send that canonicalized state into the network. Basically, we were just pre-computing the symmetry before sending it to the network. And that can definitely implement what we want to do. This is one solution. There's actually another one that's pretty like straightforward. Anyone want to make a second guess? Anyone have heard of data augmentation? Have you think of how to use data augmentation to do this? So yes.
It's like a particular training point. You could just do all the possible, or at least a subset of possible predictions to train on.
Yes, exactly. So typically when we use data augmentation, we are trying to learn, like making the network more stable, right? We perform some perturbation to the input data so that our network can generalize better. So here, if you want to use data augmentation to implement the symmetries, we can simply just apply the same transformation to both the input and output of our network, or to both the data and the label, right? We compute all of the transform version of the same data point, and then we train from all of them. That's a that's the second way of implementing the symmetry. Typically in the literature, we just call it using data augmentation. So now we have canonicalization, we have data augmentation. Both of them are great strategies for implementing the symmetry. And now I'm going to talk about the third one, which is enforcing the symmetry in the neural network architecture. I will talk about what I mean by that afterwards. So in order to do that, we will first need to define the representations of our state and action. Well, as I said before, we're more sort of like abstract concept. I said the parallel rotation to a state, a parallel rotation to the action. What does it actually mean by that? What do we actually need to do if you want to do that in the neural network? All right. So we typically define the state as a top-down image centered with respect to the gripper. Why do we do that? Because then a rotation of the state will be the same as rotating the image. That's going to make it easier for the network to recognize the rotation when we are doing policy learning from vision inputs. And we typically define the rotation to the action as rotating the XY vector of the action and leaving the other component of the action unchanged. So basically what it means is you want to reach the object, for example, right? So if the object and the gripper are rotated by the same amount, the XY action that bring your gripper to the object should rotate accordingly. So we need to apply a rotation, which is a 2x2 rotation matrix to the XY vector. And then the other action component, for example, the D action, which is like gonna bring the gripper up or bring the gripper down. That action doesn't need to change when there is a rotation to the state, right? Cool. So this is the definition of the rotation of state action, and now we want to build an equivariant version of the networks. Basically, we just need to mimic what the properties that's in the Q optimal Q function and optimal policy function. We just build an invariant network to model the Q network, and then we build an equivariant network to model the policy function. So this is going to be implemented through weight sharing using equivariant steerable CENs. This is the third way of achieving this kind of symmetry. Basically, what a steerable CEN is a special kind of convolutional neural network that is symmetric by definition. So here's an example of that kind of architecture. On the top, we have a conventional convolutional neural network. That's just the network that we use every day. We can have some input data, and it's going to give us some feature map, right? Now, if we apply some rotation to the input and then get the feature map, and then rotate the feature map back by the degree of the rotation applied to the input image, we can have this so-called stabilized view. This is going to tell us the level of equivariance that exists in the CEN, right? Because if the CEN is perfectly symmetric, the stabilized view should always be the same, because we apply rotation first, send it to a network, and then apply the inverse rotation on the output. So if the network is symmetric, we should have the same result on the stabilized view. And on the bottom, this is the equivariant convolutional network that's built from steerable CEN. You can see that the stabilized view doesn't change at all, right? So that means the network is perfectly capturing the symmetries in the input. Now, how do we actually do that? How do we actually build a network that is equivariant by default? So to understand that, we will first need to have some backgrounds in group theory and representation theory. This is this is a little bit of a little bit hard to understand, but that's fine. So we can try to think about it together. So basically, we were all talking about rotations, right? So when we say rotation, it's basically a continuous rotation angle, right? So for example, we can rotate from 0 degree to 360 degree, and it's going to be a continuous value. But in neural networks, we typically discretize things, right? So consider the images that we process in a neural network. It is not the continuous signal of an image. We break it down into pixels and then process it using discrete filters, convolutional filters. We're gonna do similar thing in the Equivariant network. We're gonna first discretize the rotation so that it's easier for the network to capture the symmetry. So we will define this group B4. This is the cyclic group that contains 4 different rotations ranging from 0 to 2 pi. So typically, it's going to be 0 degree, 90 degree, 180 degree, and 270 degree. Basically, it contains 4, these is a 4 discretized rotation from ranging from 0 to 2 pi. And the number 4 can be an arbitrary number. You can use, for example, C8. Then you gonna have 1 rotation every 45 degree in a group. It's just a different level of discretization. Like you can downsample your image, or you can have different resolution of your image. And then still in the group, a rotation is still a relatively abstract concept, right? So when we say we want to do a rotation, it can mean different things. First of all, a rotation can be invariant, right? So think about the example of the cat classifier. When we rotate the input, we want output to be the same. So invariance is also a type of symmetry, right? So when we think about that, we typically call this as an identity mapping. This is going to be implemented by a 1-by-1 so-called representation of the abstract group element. So basically what it does is for all of the angles in our group C4, it's going to map it to 1 because it corresponds to invariance. No matter what group element or what rotation we have in a symmetry group, we just always map it to 1 for a identity matrix. That's gonna help us to implement invariance. And the second one that's gonna be useful for us is the 2-by-2 representation by rotation matrix. That is when we use a group element to rotate a vector. Right? Think about you have a 2 vector. You want to rotate it by a certain degree. What you should do mathematically is multiply it with a 2-by-2 rotation matrix, right? So each rotation angle in our rotation group can be mapped to a particular 2-by-2 rotation matrix. This is the second representation that's going to be interesting to us. It's going to be useful for us because if you recall how we define the rotation on the robot action, we're going to rotate the xy vector of our action, right? We're going to use this 2-by-2 rotation matrix to rotate the vector. And then in the end, a rotation can also mean a permutation, right? So imagine here we have 4 different elements, 4 different corners on the square. We can label them with different angles. And if we say we want to apply a rotation, right? We want to apply a 90-degree rotation to the square. That means those 4 different corners are going to be cyclically permuted, right? So if you rotate it like this, the red is going to be here, blue going to be here, green going to be here, and orange going to be here. So the rotation can also be a permutation of a vector. So in our case, it's going to be a 4 vector. Each corresponds to a particular rotation angle in our group C4. And if you apply rotation to it, we cyclically permute the elements in the 4 vector. So far, so good. Right. So if we have that, we can further expand those features into feature maps, because we do want to just deal with vectors. We also want to deal with images of different types, right? So for the identity mapping, if we extend it to feature maps, basically it's just gonna be what we mean by rotating an image. What's gonna happen here is that if you apply a 90-degree rotation to the image, all of the pixels are gonna rotate, but the contents in the pixel gonna stay the same. Think about like rotating an RGB image, right? We're gonna rotate all of the pixels of the RGB image, but RGB value in each pixel not gonna change after you apply the rotation. And then for the 2x2 representation of a rotation matrix, if we extend the 2 vector into a feature map, that's gonna be a vector field, right? We can have a 2-channel image where each pixel can be represented as a vector, and then the entire image will be a vector field. If we apply rotation here, we're gonna apply the rotation to each single pixel. Taking that particular pixel as an example, we rotate it 90 degrees. It's gonna turn from here to here. But at the same time, not only the pixel gonna be rotated, the content of the pixel, the direction of the vector are also gonna be rotated. So this is the second case. And then the third case, we have the permutation, right? Here, as similar as before, we will rotate each single pixel, and we will also permute the order of the 4 different feature maps. So this is basically how we can, yes.
The 1-by-1 representation. How do you know, like, color, put in where
Yes, great. So the question is for the lab case, how do we know which color to put in each of the pixel? So basically, what you can do is that you look at all of the pixels in your input image, you calculate what each of the pixels should go in the rotated image, and then you just take that color with it to the new image. Does that answer your question? Yes. Great. Okay, great. Are there any other questions? Yes, great. So basically what we have here is that we are generating a concrete representation of the abstract rotation. And then we're gonna use it for building our Equivariant neural network. So basically we can have a network where each of the layers can have different representation. Typically on the input, we're gonna have this basic scenario where we only need to rotate the coordinate of the image, and then the pixel won't, the value of the pixels won't change. And then in the hidden layers, we can have a different type of representation. And then on the upper layer, we can have what we will want for the desired property of the output. And then if we build a network that connecting different representation together, we want to make the rotation symmetric property to permute within sorry, not permute. We want to commute within the neural network architecture. Basically, if you rotate that input image, you want the hidden layers to apply this defined transformation. Basically, in our case of 4x4 permutation, we want the hidden layer to permute and rotate. And in the end, we might want the alpha to be applied by a 2x2 region matrix. Basically, we are connecting different type of representations of the same group element together inside neural network. Great, so that's enough for for the concepts or the backgrounds. Now let's look at a concrete example of how that actually works. So imagine we want to have a layer H that maps from a 3x3 image to a 2 vector, right? So the 3x3 image are gonna be what we call, the 1x1 representation, where only pixel rotates, but the content of the pixel won't change. And then for the output, we're gonna have a 2 vector, which is the 2x2 representation, if you remember, where we want the vector to rotate by a 2x2 matrix, right? And if you want to have a filter that can achieve this kind of mapping, the size of the filter are gonna be 2x3x3, right? In the convolutional networks. So the desired property that we want for this simple layer is that when the input image is rotated, we want the output to rotate by the 2x2 rotation matrix. So consider a standard neural network or a standard convolutional filter. We're gonna have 18 weights for training this filter, right? But let's constrain the weight somehow. Let's just assume that there are 5 free weights in this 2x3x3 filter, and it is constructed in a certain way like this. Now, let's try to apply an image. Let's try to send an image to our mini network, right? Assuming we have an image I, where the first row are all ones, and the 2 remaining rows are all zeros. We send this image to our filter, we're gonna get the result of A plus B plus C negative A minus B plus C, right? Basically, it's just this part convolved with the first row of the computer, and we got the 2 vector like this. And then let's think about a rotated version of the image I, right? So as we said before, we're gonna rotate all of the pixels, but keep the contents of the pixel environment, right? So basically what it means is the first column is gonna be all ones, and then all of the other columns are gonna be 0. And we send this rotated image denoted by GI to the same layer. And then they're gonna have this, right? We convolve those 3 ones with the first column of our filters. We got A minus C plus D and A plus B plus C. And if you notice, the G is a 90-degree rotation. If you write it down as a 2x2 rotation matrix, it's gonna be 0, -1, 1, 0. And it's exactly the same as applying that 2x2 rotation matrix to the feature map that is generated from the unrotated image. And if you're interested, you can take that filter and then change the image I to whatever image you want, and then calculate what the output gonna be. It's always gonna be the same property. But as long as you rotate the image by 90 degree, or even you can rotate by 180 degree or 270 degree, you're gonna have this output to rotate in a constrained or desired way. This is basically how we implement that. We do it through weight sharing. So if you want to talk a little bit more detail about that, think about the convolutional neural network, right? So if you have thought about the property of a convolutional network, it is actually gonna be approximately translation equivalent, because the same filter are gonna be applied to everywhere in your input image, right? So imagine you think about the filter as a feature extractor. You're gonna extract exact same feature no matter where that feature is located in your input image. And so in a standard convolutional network, we can implement translation equivalence. And the way we do it is through weight sharing. We share the same filter in all of the different locations of the image that we apply the convolution. And here we are doing a similar thing. We are sharing weights across different rotations so that the same filter can capture the exact same feature in the rotated images. Okay, so that's basically that's how we can actually implement an equivariant neural network. But this is just the very beginning. There are like more detailed thing that we need to do, but I'm gonna skip that for the lecture. If you're interested, we can talk more about it offline. And now let's look at some fun stuff, the results. So here I am showing the training process of a sorry, I forgot to ask, are there any questions on the previous step? Like, let me know if you have, classification questions or whatever. That yes, please.
In order to like actually capture all the, like, I guess the rotations, do you have to just basically use like spectrum of kernel sizes such that it like translates throughout the entire extension? I don't know if my question makes sense.
Sorry, you mean like, do we have to have larger filters so that we can capture the same feature?
Yeah.
Exactly. That's a very great question. We do. We need to have larger filters. But it's worth it. So okay. So the short answer is yes. We need to have a larger. Typically, it's going to be twice the size of what the original network is going to be. But the thing is, if you want to, so some people might think, okay, this is bad. We don't want larger networks. But if you think about like just solving a problem that is symmetric, you will need to learn the symmetric property in your problem anyway, right? In the end. So some capacity of an unconstrained standard network will need to learn the symmetry. But in our case, although the network is larger, we are constrained to have the predefined symmetric property, which is better than learning from data. Because even though you have those extra capacity in your network, it's not going to be guaranteed that an unconstrained network can learn the symmetries. But here, for the larger network, it's going to be guaranteed to have that problem. So yeah, so that's a great observation. We do need a larger network to do that. Great. Yes.
In the beginning, I think you said that both the reward and the input state or the transition function input can be invaded and failed required an equivariant network as such. This means the input state is like the making sure that all the input states are good. How are you assuming that the dynamics of the reward function and the transition function are the same?
The dynamics of the property or the symmetries in the reward function or the transition function.
Let's say the symmetry.
Yes. So okay. So the question is, are we assuming that the symmetry in the transition function and the reward functions are the same? Is that right? Yes. The answer is yes. So we are assuming that the symmetry that exists in the transition function and reward function are the same. So if we go back to definition, here, those G are actually the same rotation. The G's in both reward function and the transition function, that's the exact same rotation. And they are also drawing from the same symmetry group. So for example, in our previous example of C4, where we're only considering 4 rotations, that G is going to be one of the 4 discrete rotations. And if you are considering continuous rotations, those G are going to be still going to be the same rotation, even though it's going to be randomly sampled. So yes, that's a great point. The symmetry that we are assuming in both functions are the same.
Any other conditions, aside from rotation, like maybe shrinking or like growth, like
great. Nice question. Yes. We are considering all of that. So for the first part, I'm gonna be talking about rotation symmetries, and then in the second part of the slides, there will be translation symmetry as well. But I already mentioned that, if you consider a standard convolutional neural network, it already has just translation symmetry. So all we need to do is to put the rotation symmetry on top of it. And then you also talk about shrinking. I guess that we can also call it scaling, right? Scaling equivariance is also a very active field of work. Basically, we can think of like if the object is bigger, we should open our gripper more. If the object is smaller, we don't need to open that much. We just have a smaller open base. Yes, that's a great point. Also, I can briefly talk about like there's a paper, I guess 2 years ago, they were using 2 arms to do some cloth flipping. They want to unfold, let's say, a t-shirt by like just doing a flipping. Basically, they were using scaling equivariance there because if you have a larger fabric, you want to extend your 2 arms further away to do that, to do the fling. If you are facing a smaller fabric, you wanna like shrink the distance between your 2 arms to be the same, like transformation or scaling transformations are going to be applied to the fabric. Yes, so all of those are valid symmetries that we can consider in the network. But here we are mostly considering rotation. That's the most obvious one and this easiest one. That's a great question. Okay, great. Now let's look at some results. So here I'm comparing a conventional actor created method versus our version that has the symmetries embedded in the network. So this is the learning process of the 2 agents. On the top left, I have number of steps, number of episodes, and the success rate over the previous 20 episodes. Good. Yeah, the success over the previous 20 episodes. So if you look at the video again, at the beginning, most of them are basically just doing random exploration. Sometimes it can get lucky to pull the drawer open. Oh, by the way, I forgot to say the task is drawer opening. The robot wants to open the drawer. And then you can see the equivariant stack, which is our version with the symmetry. After 1200 steps, you could reach a 100% success rate. But this conventional version built with standard neural network can only reach a 20% success rate. This is a dramatic improvement in simplification.
What constitutes?
Oh, the success means the drawer is open.
It's just terminating the failed efforts.
Yes. There's gonna be a maximum amount of step that they can try, and the reward is a sparse reward that's only given when the drawer is open. This is the simulator. We can check whether the drawer is open or not by reading the joint in that drawer. And then the action space for the robot is the XYZ delta movement, like basically a relative movement from the current state, as well as the relative rotation, top-down rotation. And then the state space is actually the top-down image that I mentioned a couple slides ago. Great. And then here are some quantitative results. This is the learning curve. I guess maybe some of you in your final project gonna be drawing those kind of curve. The x-axis is the number of training steps, and the y-axis is the evaluation discounted reward. It's also calculated return. And then the blue curves are our method, and then the other colors are the other state-of-the-art reinforcement learning methods using different methods for improving the sample efficiency. We can see that the yellow baseline is the only one that was able to solve the block pulling task, and in all of the other 2 tasks, our method is the only one that can solve it. It's a dramatic improvement over the baselines. And then, yes. Yeah, great. The question is, does the state only contains the XYZ of the gripper, or it also contains other joints? the state, we are actually using visual inputs. The state is a top-down image centered with respect to the gripper, which is this. So this is the state that the network is seeing. You can roughly see where the gripper is in the center of the gripper. In the center of the image, and you can also see the object in the world. But we don't really use the ground truth state, which is the position of the object or the position of the gripper. We use this vision input. Yes.
How do you handle the control over the Z coordinate when it's just provided a compound?
Great question. We were using depth images.
Using what?
Depth images. In RGB image, each pixel is the RGB value. In a depth image, each pixel is its distance to the thing in front of it. So in our case, it's going to be a table. So in each of the pixel, you can see how far it is from the table.
So there's no like RGB in place, just distance. That's all it's given, or is it given both?
Yeah, the question is, does it have RGB or only depth? It's only depth, but you can also do RGB. Yeah, we were using depth only. I don't know. By the time we were doing the project, we just thought depth is a better input. There's less noise, and also if you want to do sim to real translation, it's easier. In the real world, what you can see from a depth image is typically the same as what you can generate from a simulator. But if you think about RGB images, your object can have different color, the lighting condition can be different, so there will be a larger sim to real gap. So we prefer to use depth image.
It's just like a speculative question, but if you were to include RGB, what are your thoughts on finding symmetries within colors?
Yeah, great point. The question is, if you are using RGB images, how can we find the symmetries in the RGB image? So in this particular example, you might already notice that there are 4 different coordinates in the workspace, and they have different colors. This is actually definitely going to be problematic. But generally speaking, if we are working on, let's say, this table, it has the same color across all of the areas, right? We all have those 4 different colors just because in simulator it's easier for us to debug. So most of the case, the symmetry actually going to be the same. What you have when you have depth images, the same symmetry going to be applied to RGB images. So typically you can just directly use it. And then another solution, I'm going to actually cover that in the second part, which is what if there's this mismatch, right? So if you rotate the left image, it's not going to be the same as rotating the state, right? Because when we think about rotating the state, only the object should be rotated. The fixed background in the image won't rotate. How do we do with that? I'm going to be covering that in the second part, but short answer is that you can ignore it. You just still use the same symmetric network. It's not going to work. Yes.
Talk more about the arm itself in the state space.
Sorry.
You have not included the arm itself in the state space.
Yeah.
It's like does that help communicate with resolving the symmetry? So like the arm, that the actual arm might not lose.
Yeah. Yeah. So the question is, we don't see the arm in the state space, right? Why is that? And is it because the arm itself is not symmetric? The answer is yes. So if you think about the ultimate correct way of doing that, the arm should rotate when we rotate the state, but that's not going to happen, right? Typically in robotics, we have a fixed robot base, and then but the world in front of the arm are going to rotate. So what we do is that we exclude the arm from the state space so that we only consider the transformation that happens to the object as well as the gripper. Another way of thinking about it is you can think about we have a floating gripper without all of the joints. We just have a floating hand in the workspace. And there we will have the perfect symmetry. And with the joints that's connecting the hand to the base, there will be some, we call it symmetry breaking factors, because there might be some area in the workspace that's not reachable by the arm. And if the symmetry in the network is asking the arm to go to that particular position, it's gonna fail. And this is actually ongoing research in our group. And that's a great question, by the way.
So you're saying you're considering having a floating hand and then you're doing the math to figure out what you need to do to operate, get that block in that?
Yep.
Okay.
Yeah, that's right. That's right. So we basically we call this end-effector control. So you only command where the gripper should go, and then there are softwares that can tell you how the drawing should move in order to get the hand to your desired goals. We typically ignore that part. We just use some of the existing tools for doing that, and we only consider where the hand should go. Right. Yeah, thanks all for the great questions. I really appreciate it. Okay, so we were testing in those domains. We got great results, but those tasks are somewhat easy. So we also try some harder tasks like block stacking that, it's not just picking something up. You actually need to do a relatively precise placing to stack it on top of another block. And then there's house building is similar. Maybe it's too small. I apologize for that. The house building is picking up a triangle block and then place it on top of the red block. And then corner picking is that there is like a corner, static corner in the word, and then the arm need to tackle the object out from the corner and then pick it up. In those more challenging tasks, none of the baseline can work at all, and our method can still solve them very efficiently. And then, yes. Yes. Yeah. Yeah, that's a great question. The question is, if we only have a top-down view, right? And if one block is on top of another, we're gonna have occlusions. You won't be able to see the bottom block. This is a very important issue that we're gonna face when we have this top-down image. But to the extent of this work, we can ignore it because first of all, there are only two objects in the world. So if you don't see the other, you can assume that the other one is beneath one is beneath another, right? This is still Markovian, so it's not gonna validate that. Another thing is that the two blocks are not gonna exactly be on top of each other. There will be a little gap, and then you can kind of learn that from from that gap. And moreover, you can also incorporate some histories in the observation space. So if you guys have looked at the DQN for playing Atari games, they were using history frames as the state space. We can do similar things here. We can incorporate, like, for example, one previous time step or even more, so that it will kind of see the trajectory and you will have a better sense of one object might be below another one. Moreover, you can also think about some 3D vision. I don't know if you guys have heard about point clouds. It's a 3D data where we're gonna store like the points that represents the surface of the workspace or object, whatever. Or we can use voxel grids. Those are, the other solutions to combat that problem. But this is actually, it is a problem that we're gonna be facing. Yeah. Sorry, you were speaking a bit fast. I do. So you mean like why are we using top-down view, or can we use other view?
Yeah, there's any advantage in the other view, or do we feel like it's sufficient to just like top two can accommodate all the credit?
I see, I see. Okay. So will there be benefits of using a second view, and this top-down view enough? So the shorter answer is for those easy tasks, the top-down view is enough. We actually didn't use any history step. We just have one step of observation, and it was sufficient for solving those tasks. But it's definitely going to be beneficial if you have another view. But when you are incorporating the second view, you need to think about how rotation applied to your second view. You cannot just use an arbitrary view. For example, if you just use a viewpoint, like what images that we are showing here, it's not gonna, well, it could work, but you are facing what we call symmetry mismatch problem. Because if you have a top-down view, you rotate the image, that can correspond to the rotation of the ground truth state. But if you rotate this image, it's gonna be different, right? In the second part, I'm gonna be talking about that problem a little bit. But just something you need to think about when you are incorporating different views. A solution could be using a wrist mounted camera. You mount the camera on like just on the wrist of the gripper. They cannot see both the gripper and also the scene. Basically, that image you can think of it as an environment image, because if you rotate your work, what you're gonna see in the wrist mounted camera not gonna change. But yeah, that's a great point. So it's definitely gonna be valuable to incorporate a second view or even more views, but we just need to think about how the rotation gonna apply to those views. Yes.
Just to add on, what possibly could be done is like multiple cameras could be used, just get an understanding of the environment that goes. And once you have the positions of everything in the environment, you can transform them top down.
Ah, I see. Yeah. That's a good point. So the comment is we can use multiple different views to try to understand the world. Let's say we can maybe build an encoder of it that encode our world into some hidden state, and then we start using symmetric networks from there. That there is actually a paper that did that. It's called symmetric embedding network. So this is a great comment. This is something that we can do. Yes. Great. Right. So those are. Oh, sorry. Yes. All right.
I just said the block setting or transformation with but then it on how we will be for the performance of coordinated on the other side, maybe. But if you started training the already trained block setting agent on the house, that's how will it
Oh yeah. I guess the question is, can we transfer? Can we transfer the policy learned from block cycling to house building? That's a great point. I didn't try it. I only did this learning from scratch, but that could be your final product for the course. But that's a great point. I think it's gonna help. Yeah. All right, great. Yes. Oh, those question is, are the size of two blocks in block stacking the same? Do we stack larger ones on top of smaller ones, or stack smaller ones on top of larger ones? So in fact, here the two blocks have the same size. It doesn't really matter which one goes on top, as long as those two are, one is on top of another. That's we will have a reward of 1 for that. Oh, I see. So if the size of the blocks are different, but they are different in a XY extent, then that's fine, because, well, I guess even though it's different from the Z, you can see it from the depths, right? So I think it should still work. We just didn't consider that scenario. But I guess it's gonna be, I I think it could be easier actually if the two blocks are different sizes, because here you might have a multimodal problem, because the agent actually need to figure out, should I go to the first block or should I go to the second block? But if the two blocks have different sizes, there's no problem like that. It's easier to distinguish which object they should go for the at the beginning. The house building. The house building is picking up a triangle block and put it. Oh yes, yes. That's similar to a large and smaller block. Yeah. Yes.
Considering like it's a triangle from a top-down view, isn't it like literally the exact same as block stacking? Why is it any different?
It's not actually. It's not the same. So you're gonna see like two slopes in the depth image.
Oh, okay, yeah.
Yeah. And then the other difference is that for the block, you can pick it up either like this or that. But if it's a triangle, you cannot like grasp the slope. You need to grasp from a stable, like the perpendicular side. So that's making it a little bit harder. You are not?
Yeah,
Yeah.
I was just wondering, would it be possible to incorporate like a memory for this role so that it would know, like, if you put something on top, that there was still, like, from just observation, that there was something.
Yes. I think that's good. So, so for those tasks, it's actually not needed, but I think that could help. Yes. Okay, great. All right, let's move on. So this is great. We got great results, but it's still boring. It's in the simulator, right? Everybody can run simulator for a long time and then learn a policy. So next thing we do is actually learn on the real system directly. So here we were considering 4 different tasks. The block picking is same as before, and then the pushing is requiring the robot to push the block to a particular goalpost in the world, and then the clutter grasping is picking up one of the objects from the clutter, and then in the end, blocking ball is a pick place task. The robot needs to pick up a block and then place it inside a ball. And then we were able to train an RL agent from scratch in those 4 different environments. So recall that in the beginning of this lecture, I was talking about the work from Google that I trained for like 8 months or whatever. We can actually do it within 1 hour. So the first 3 tasks, we actually only need less than an hour to solve it with higher than 90%, but 90% success rate. And then the last one, blocking ball, requires slightly longer. That's mostly because this is reinforcement learning, right? We need to find a way to reset the environment. In the simulator, we just call reset, then boom, everything goes away. We can create a new environment. But in the real world, we cannot do that. We need to ask the robot to reset the environment by itself. So that's going to take a lot of time. So for the blocking ball, you actually need to reset both of the objects. So it's taking a lot of time, and then it needs like 2 hours and 40 minutes for doing that. And then we also run a comparison against one of the state-of-the-art baseline in 2022, and then we were significantly better than it. So here is a training process of the clutter grasping task. You can see at the beginning of the training, the agent is just doing some random exploration. And after a while, it's going to reset the environment. And then finally, it got the first success grasp. They pick up the blue toy. And starting from there, it gradually improve its policy. It's picking up objects faster and faster. It's having some trouble with the monkey. And then in the end, it can very stably pick up the objects in the bin. Okay. Great. So yeah, question.
For the clutter grasping and for the blocking board task, are the holes in the containers fixed to the ground, or do they move as well?
Sorry, can you answer
So, is the blue like the ball or it's staying here and the ball in the other time fixed to the ground or can they move it?
Uh, you mean, can those beans, the blue beans move or not? No, they cannot move. Those are static. So we tie those two beans on top of the table. This part of the environment they cannot move. So the workspace is within the center of those two beans. So actually, we build this two bean setup. But during training, the workspace is going to be one of the beans, and then the other bean is used to reset the environment. So, for example, in this task, every time the robot pick up an object, it's gonna drop the object in, we call it reset bean, which is the other bean than the workspace bean. And then once all of the objects are picked up from the workspace bean, it switch to the other bean and repeat that process. So if we look at the video again, you can see it start from the right bean, right? And then after it pick up an object on the right bean, it's gonna put it on the left. And then now the workspace is the left. Then it pick up an object and it's gonna put it on the right bean. So this is just a way of resetting the environment. Yes.
So while setting that environment, is it learning during that period or is it not?
No, it's not learning from resetting the environment.
Learn from that, but literally there is a symmetry between the builds and you can actually use that data for learning as well.
Yeah, that's a good point. So yeah, we could learn from the resetting as well, but we just simply hand code the reset policy and then just execute that. We were just trying to mimic how a person can reset environment. We just didn't really want to mess up with the object ourselves. So we just did it, ask the robot to do it by itself. But you can definitely learn from the reset, and that's a great idea.
Like run so slowly? Is it just a limitation of the robot or is it a safety based measure?
It's actually not that slow. I guess I just, yeah, this video for the paper, I just try to make it within 2 minutes. But yes, if you wanted to move very fast, there will be more engineering concerns like safety or whatever. But since we define, let's say we define the step as a movement in the range of -5 centimeter to +5 centimeter, that you can move at most 5 centimeter away. But how fast you move to that 5 centimeter goal is something that you can tune from the engineering side. Yeah. Cool. All right. So that's for the first part. The first project is Equivariant, actual graded methods, and we were showing great improvements by incorporating symmetries in the actual and the graded method. And we also tried to actually learn the policy, RL policy from scratch in the real world. And now I'm going to talk about the second project, which is Equivariant Q learning, or you can think about like Equivariant QN. So if you so the lecture is until 4:30. Oh, okay. Yeah, it's short on time. Okay, so if you recall the last project, the action space were defined as the delta movement of any factor. You can define like, move along the x-axis for 5 centimeter or whatever. And there's actually a second way of defining action, which is commanding the target pose of the any factor. So in the instead of doing those step movement, we just tell the agent where to go directly and then just ask the robot to execute a long action. This is similar to the question that you were asking, right? So this way it's gonna be faster. So both of the formulations have pros and cons. If you are in the so-called closed loop where you control the individual steps, you have the chance of correcting your action. For example, you pick up an object and then you drop it. You can instantly know that you dropped it and then you go back to pick it up again. But if each action is a complete pick action, and if the pick action failed, the agent is still gonna finish what's commanded later than the grasping. And then you need to like correct a action much slower than the first scenario. But both of them have pros and cons. This one is going to be faster, and each action step can move the robot longer so that it can solve more challenging tasks within smaller number of task steps. But anyway, the symmetry still exists in this setup, right? So if I rotate the object, I will want my action to rotate accordingly. This is the same as before. Actually, here we do have this SC2 equivariance, but before we will only have SO2 equivariance. This is because if the object translates, we will want the robot to translate its action, to translate where the gripper are gonna be moved to. Okay, and then if we recall, in the symmetric MDP, the optimal solution for the MDP, which is the optimal Q function, should be symmetric. We define it as an SC2 invariant function, but in DQN, a Q network is a mapping from state to the Q value of all of the actions in the action space, right? So the Q network in a DQN is going to be different from the credit network in the actual credit method. In the actual credit method, the credit takes in both the state and action, and it output a Q value. So this is the same as our definition of the optimal Q function. But for DQN, the definition becomes a mapping from state to action, state to the value of all actions. So we need to change the formulation of our neural network accordingly. So basically what it means is the invariance in the Q function becomes an equivariance in the Q network. In this Q network, if our state is rotated and we were estimating the value of the action A, it's gonna be the same as passing the original state to the Q network and then curving for the value of the inversely transformed action G inverse A. So I'm gonna give you an example now if this seems confusing, right? So imagine we have this top-down image of the world, and then the goal is to pick up the orange block, right? And then we estimate our Q value, estimate our Q network about all of the possible actions in the workspace, the value of all of the possible actions. The output of the Q network are gonna be a set of 4 different Q maps, and each pixel in the Q map correspond to a particular translation of the gripper. Basically, just each pixel correspond to a particular grasping position in the workspace. And then we have a set of 4 channels of the Q network. Those 4 channels correspond to 4 different rotations of the gripper. For example, the first Q map corresponds to picking up the object like this. And then the second Q map corresponds to picking up the object like that. So they all correspond to a different rotation. And now, what if there is a rotation on the input image, right? The first thing that should happen to all of the Q maps is that they should all rotate accordingly, right? Because the object got rotated, we should definitely rotate the translation part of our action. But what's more is that what was originally the 0-degree rotation now becomes the 90-degree rotation in the rotated state. And what was originally 90-degree now becomes the 180-degree rotation in the rotated state. And similar mapping applies to all of the rotations in our actions. So what that means is that the order of the Q maps should perform a circular shift, right? So let's say that the optimal action was 0-degree rotation at that location. Now, in the rotated state, the optimal action should become the 90-degree rotation at this rotated position. This is the desired property that we want in our Q network. So if you recall, this is exactly the same as what we call this 4x4 permutation, 4x4 permutation representation of a group C4, right? So we can basically just use that to build the equivariant network. And then moving on, we have some results here. we have for like more challenging tasks than before, but this is mostly because each action is a longer sequence of motions, so that you only need to perform a certain number of pick or place actions to finish this more challenging task. And we were considering this house building, even though it's still called house building, but it's much harder than the last house building. Here you actually need to align those two red blocks and then put the blue on top, and then align another red and then put the roof on top. And then we have COVID test. I don't know if any of you, yeah, I guess you guys were not here when COVID hit, but at Northeastern we needed to do COVID test every week or every 2 days. And then I was this paper were done at that time. I was mimicking what need to happen for the COVID test moderator. And we also have box palletizing, which is stacking 18 box on top of the pallet. In the end, we have beam packing. And similar as before, we were doing much better than all of the baselines. Our results were in blue. And then the green line here is the same as our method, but just with non-equivariant network. So simply by replacing the equivariant network, simply by replacing the standard network to an equivariant network, we can get from green to blue, which is the dramatic improvement. Yes. Yes.
Does it mean that like Q networks are better than active?
That's a great question. I wouldn't say that's because Q network is better than active. I think this is mostly because of the different action formulation. So in the last paper, each action is a delta movement of the end effector. So in order to perform a pick, you might need to do, let's say, 10 steps from the current pose to where you pick up the object. But here, that's only one step. You specify where the gripper should go, and that one step, you reach the object. So within the same amount of step, this formulation can finish more complex tasks. But the problem of it is that it's harder to recover from failures. So let's say you fail to pick it up, but you're still gonna finish what's commanded after the pick action.
How did you, sorry, can you restate the action formulation?
The DQN is the target pose of the gripper.
You just like discretize it with like a certain.
Yes. Great point. We do discretize it. It's the same. The first of all, the translation part is the same as the resolution of the image. So let's say we have a 128 by 128 image, then each pixel will correspond to a particular position in the action space. And then the rotation, we have another discretization. Let's say if you use C4, it's on before, but in the experiment, I believe we use C8 or C16. So there were like 16 rotations ranging from there to back. Cool. So yeah, so this was great. And we did another on-robot learning using a similar formulation. So here we were trying to learn grasping. We formulated as a bandit problem. So basically a multi-arm bandit problem. Each of the action, same as before, is a target pose of the gripper. And then after you execute the grasp, you will know whether the grasp is success or a failure, because you can read the open base of the gripper. If it's not 0, that means you pick something up. If it's 0, that means it's nothing. So that's a failure. And then we were training it directly on the robot, and we were actually able to solve this problem within 600 steps, which is approximately an hour and a half. This is significantly faster than what others can do by the year of 2022. And then the video we're showing the learned policy in some novel objects, which means those objects that we are testing on were not seen during training. So it could actually also generalize to novel objects very well. It could actually reach a 95% success rate in those unseen objects. Okay, great. Yes.
So, yeah, sorry to kind of ask you there. I think we should try to wrap up in the next couple of minutes, but I think one question before that, I think what was asked earlier, is that essentially you've kind of presented two slightly different approaches, to get to a fairly, similar point, right? So do you have any kind of overall comments on like, which kind of acting space is better, which kind of approach is better? Like if like someone here wants to deploy it in their lab, which is the thing that they should first try to do?
Yeah. That's a very good point. I don't really have a preference over the two methods. So first we talk about actual credit methods, and then we talk about this open loop action space. I think both have pro and cons. But I would say the UNet, the second part of the DQN is actually easier to implement because typically actual credit method were harder to tune. There were more hyperparameters that you need to play with. You also get it to work. But DQN, from my experience, was very stable. The only loss you apply is the TD loss, right? And then normally you won't hit any like gradient explosion problem. So I would say if you are new to deep learning, starting from a DQN would be a great starting point. Also, I like the DQN because you can actually leverage SE2 symmetry there. Because a convolutional network has translation equivariance by default. It's not perfect translation equivariance, but it's approximate. And if you also add the rotation symmetry in the network, then it got extremely powerful. I'm not sure if you guys have heard of UNet or fully convolutional network. Basically, it's a network without any FC layers. All of the layers are convolutional layers. People typically use this kind of network for semantic segmentation, or what other tasks we use that, or diffusion models, I say. So it's a very common architecture and it's very mature, and you can get a great benefit by leveraging symmetries there. Yeah. So if you guys are interested in this line of work, as we about on time, if you guys are interested in this line of work, we actually have a library that contains all of the methods that we have developed. It's called Bullet Arm. Yes. So it's called Bullet Arm, and then it got all of the environments that I was talking about in this talk. Yeah, here. It got all of the tasks that I have been talking about, and also all of the benchmarks or methods that I was describing. So yeah, so those are the closed loop tasks that is in the first part of my talk, and then those are the open loop tasks, which is in the second part. You can see this house building, this complex house building task, right? And we also have all of the methods implemented in the library. So if you are interested, you can try it out yourself, or even use it for a final project. Yeah.
Still not too late, I guess, given that it trains in an hour or something.
Yes. The good thing about this kind of thing is that once you have the math right, once you have the architecture right, it just got trained very fast. It's very satisfying when you see it's actually working, and it's gonna beat all of the baselines. Okay, so I guess I will skip the other parts, which is fine because the main part is the first part. The other parts were not very related to reinforcement learning. So if you want to learn more, you can try to visit my personal website that contains all the papers I was talking about. And there's also a link to the Helping Hands lab, which is the lab page of Professor Robert Platt, and then the Geometric Learning Lab, which is the lab page of Professor Robin Waters. Professor Robin Waters work on the symmetric machine learning, and without him, I wouldn't be able to work on any of those. And then same for Professor Platt. I took this class with Robert Platt, and then started working with him after. And in the end, if you have any question, you can reach out to me. Here's my email. And if you are interested in doing research with us, please reach out to me. We had many master students working in the lab with master project or master thesis. And then, if you are interested in pursuing a PhD, I believe that's going to be, a great start. That's how I started. And in the end, I'd like to thank a lot of my co-authors in the papers I've been talking about today. I wouldn't be able to do it without any of them. And yeah, it's been a great lecture. Great to see you guys. And if you have any questions, please let me know. Yeah, thank you.